That's so fun. No, I'm. Oh my God. Say no. But I'm not gonna say that. She was like, yeah. You know what? It's my picture. You're still not. Oh.
All right. We're going to start quiz review today. So, yeah, your quiz will just basically be going over these integral rules, and a lot of them are going to be U substitution problems, and we're just going to practice through these. These are topics that we've covered since last Tuesday. So natural log integrals, e to the x integrals, and log base a integrals. Okay, so we'll have today and tomorrow to do full quiz review, and then I'm going to flip Wednesday and Thursday. We'll cover 6.3. We can do a little bit more quiz review, and then quiz will be Thursday. Let's go to page 9. Okay, let me just go through the integral rules here at the top of the page. So u to the n du, that's just power rule. So u to the n plus 1 over n plus 1 plus c. Integral of 1 over u du, this is just natural log s value of u plus c. And then the related rule from first semester is we know the derivative of natural log of u is u prime over u. Integral of e to the u is just e to the u plus c. We literally are not changing anything to the rule. There's no natural log. There's no changing the exponents. It is literally the exact same thing. And the reason why is because first semester, we learned that the derivative of e to the u is just e to the u, right, times u prime, because there's a, if it's anything other than an x in the exponent, then we got to keep track of the leftover terms. But essentially, no changes. Now, tangent, cotangent, secant, and cosecant, these are not rules that show up in the original 6 integral rules that we learned. So the way I remember this, there's a way to arrive at this rule using converting to in terms of sine and cosine. So we know that sine is the same thing as we know that tangent is the same thing as sine over cosine. And if we were to think of this problem as the integral of sine of u over cosine of u du, u substitution of cosine will allow the sign to cancel out, ends up being 1 over u du, and then the negative is going to show up. So I'm not going through that full proof here, but basically the u substitution of our cosine is going to lead to 1 over u du, which is natural log, and then the negative will show up because cosine's derivative is negative sign. So this ends up being negative natural log absolute value of cosine of u plus c. So we do need to memorize this rule, but makes it a little bit easier to understand why this ends up being cosine, because technically we're doing u substitution with the cosine being the u value, since sine over cosine is just another variation of tangent. Likewise, cotangent can be thought of as cosine over sine. And if we were to go through u substitution with this starting point, then our u value will be sine. So we end up with 1 over u du, which is natural log of u. And then the sine comes back in, and this ends up being natural log absolute value of sine of u plus c. Secants, we don't really have a proof for this, but the integral of secant looks a lot like, or involves the same functions that we would see with derivative for secant. We know secant's derivative is secant tangent. And so those functions will show up, but then just in this form: natural log absolute value of secant of u plus tangent of u plus c. And then cosecant, similar form to this. Cosecant's derivative, we see cosecant cotangent, but for the integral, it's going to be cosecant plus cotangent, and the sign is going to be a negative in front. So negative natural log absolute value of cosecant of u plus cotangent of u plus c. And then a to the u du, this is base 2, base 3, base 5. Exponential functions looks a lot like e to the u, but there's conversion that has to happen. So conversion is natural log of a, but then for the integral, it's in the denominator. So 1 over natural log of a times a to the u plus c. So essentially, similar to e to the u, the original function is going to show up unchanged, but there's a little bit extra in front. Okay. So today in class, we'll just see if we can get through pages 9 and 10 for our quiz review. And I have the key attached near the back of the packet. So if you're working ahead, you can check your answers. All right, so number 1, we always want to consider, can we just rely on the expansion power rule? But as soon as we see multiple terms in the denominator added, we know that we can't split up. It's too complicated for algebraic stuff to do that. So we're looking for u substitution. And typically, if we're trying to find a u value and you're choosing between numerator and denominator usually is a better fit for us. So and that degree is also where we want it to go. So we'll let the u value be 2x plus 3. We're trying to turn this into an easier problem. We're trying to make it match one of these rules here. So with u substitution, we're trying to create an easier problem, and we're trying to make sure that our x's go away. If we want to commit to u substitution, we need everything to be turned in terms of u. So we want to replace the dx and the 2x plus 3. So we have 2 dx equals du. So therefore dx equals du over 2. So there's my terms I need to substitute. I like to pull that 2x plus 3 out so it doesn't get into a complex fraction form. All right, so I'm going to replace dx with du over 2. I'm going to replace the 2x plus 3 with u. Let's see what happens. 1 over u times du over 2. This cleans up nicely. We can pull that 2 out as 1/2. Yeah, that's right. Yes. Okay, we have a match here. 1 over u is natural log. And then finally replace the u back in terms of x. All right, try number 2. See if you can follow the similar procedure for number 2. And then we'll check our answers after you guys try it. Try number 2. Okay, we target the denominator as our u value. Dx gets replaced with du over 8x. The x's cancel out. That's what we need. Keep track of our coefficient, 1/8. Matches a nice rule that we have. 1 over u du is natural log. So we take the antiderivative, the integral notation drops out, du notation drops out, and then replace the u back in terms of x. Any questions with 2? All right, number 3. Number 3 is a little bit different because notice that there's only one term below. We should be able to expand this out, right? So no u substitution here. This doesn't say, if we try u substitution, we're going to get stuck. It's not going to work. So there's only one term below. We should be able to split this up. And the advantage here is now we can treat these like two independent problems rather than one connected problem. So 2x over x is just going to be 2. That's just going to be a nice power rule on its own. And then minus 5 over x, which is really the same thing as 5 times 1 over x dx. So this should just be a natural log rule, right? 1 over x dx, which is essentially the same thing as 1 over u du, but then without the need for u substitution. So power rule, let me write it a different way here. Maybe this is cleaner to look at if you want to split this up into two problems. The first is just power rule. Second, the 5 is a coefficient. If I push that out in front, 1 over x is just natural log absolute value of x plus c. Okay, number 5. It's true. Oh, sorry. I'm going to skip number 4 for now. We'll come back to this one. But I want to show a different problem before I work through that problem. So number 5, I know we only see one term below, but natural log of x is not in the same family as x. It's not like we can just split this up and go through power rule, because that natural log requires a different rule. So we know this is not the same as number 3. We have to go through u substitution. And our u value, we do see a set of parentheses, so let's target that as our potential u value. So we're hoping that after u substitution, the x in its denominator will find its way to get canceled out, and that we're left with something that will match one of these rules that we have. All right, so derivative du dx. We know natural log of u is just u prime over u, so 1 over x. Cross multiply, dx equals x du. Make our substitutions. Natural log of x gets replaced with u. Dx becomes x du. And then the x in its denominator. X's cancel out. And we're just left with u squared du, which is a nice clean power rule. So now we just apply power rule. And then bring back your x variable. Right, number 6. We do see a set of parentheses. Well, first off, too many terms in the denominator. We can't expand this out. You may be tempted to want to FOIL or distribute this through, but here the parentheses are here to kind of help us. It's there to indicate what the u value could be. Because if we expand this out and let the entire denominator be the u value, the derivative will produce something that will be an x at least an x variable left over, and there's no other x's in the problem that's going to match and pair up. So we do need to kind of strategically pick our u value in the hopes that the derivative will match up with the leftover terms, right? So we do need to kind of have something in place because we know that this derivative is not going to just go away to just be a coefficient. There's going to be a variable left over because we see radicals involved. Okay. Let's get that root x ready for power rule. U dx. 1 goes away. X to the 1/2 is just power rule. Now, before I cross multiply, I would like to maybe do a little bit of cleanup on this side of things. I just like to get my negative exponents cleaned up. All right, cross multiply. We have dx by itself. Let's go ahead and replace dx with our expression, and then replace the parentheses with u. And we're hoping that this root x will just go away on its own. Let's see. So ds gets replaced with 2x to the 1/2 du. We know x to the 1/2, the same thing as square root of x. X to the 1/2 and root x are the same thing, so this goes away. Pull the 2 out in front. 1 over u du. Okay. What rule is this? What rule do we use for 1 over u? That's the natural log, right? But what if this was a different power? What if this was like 1 over u squared? Can we still use natural log rule if it's 1 over u squared? We got to bring it up and go through what? Go through power rule. Okay. So just be careful that the tendency that students have is we're going to get so comfortable with that u in the denominator, we're going to assume that every u value in the denominator is going to be natural log, but pay attention to the exponent. If it's any other exponent, we got to do a different rule. We got to bring it up and go through power rule. So just want to point out that potential trap that you may experience. We only do natural log if it's u to the first power in the denominator. Okay, so 2 natural log f value of u plus c. Then replace the u back in terms of x. Sorry, this x here, 1 plus root x. All right, back page. All right, number 7. We know this is not expansion, power rule, too many terms in the denominator. If it was just x, we can split it up, but that x minus 3. We talked about how there's a certain look to these types of problems, right? Where the degree in the numerator is potentially higher than the denominator. And this type of a rational function is basically going to be an indication that we use synthetic division. Okay. So the goal of synthetic division is to take something that we can't quite split up on our own. We need some help, but the goal is that we do want to split this up into easier terms, just like how we do with an easier problem. But we're going to use synthetic division to help us split them up. And as we split them up, we'll have a much easier time identifying rules of basically 3 smaller problems rather than one large connected messy fractional problem. Okay, so this is a synthetic division problem here. Okay, both of these will be. Okay, so the indication that you have synthetic division is that your degree in the numerator is going to be the same, if not higher. And their denominator is just going to be like an x plus 3, x minus 1, just a linear expression. All right, so here's our strategy. With our synthetic division, you're going to set your denominator equal to 0. You're going to find your critical point. So you're always going to set equal to 0. You're always going to take the opposite sign of what you see inside your denominator. All right. So you're going to take 3 outside the half box. And we're just going to represent the coefficients of each of our terms. Notice we got to be careful. If it skips a degree, we need to have a 0 as a placeholder for that degree. So x squared as a 1. Negative 4x is negative 4. And then the 8 is the constant. So we bring the 1 down. Multiply. And add. Multiply. And add. Remember, you're dividing this x squared by x, so all your degrees will drop. So what started with x squared is now going to begin with x. So I have a linear, followed by a constant, followed by, and then this is not a 0, so this is my remainder here. So your remainder means I can't divide any further. That x minus 3 will stay with my last term. Now, I want to make sure that we haven't done any calculus yet. This is not our final answer. Synthetic division is just so that we have an easier time finding integral rules. So if you look, we started with a messy, complex rational function, and now we're left with 3 independent terms where we can find the integral. So then to the side here, let me indicate what I want to do. I want to find the integral of my problem here. And the nice thing about synthetic division is that it's always going to end up with just the first few terms being power rule, and the last term will be a natural log. So x becomes x squared over 2. 1 is a constant. Remember, doesn't go to a 0. This is the antiderivative. Every degree rises, so a constant will rise up to degree 1. And then it's a little bit of u substitution here, but if you understand that the x minus 3 is just the u value, it'll just be 5 times 1 over u du, which is 5 natural log of u plus c. And then the u is x minus 3. So if you want to go through a full u substitution, you can, but you can also jump directly from here to here if you're comfortable with that. Okay. Try number 8. See if the steps that we just went through for number 7 make sense. Okay. When you have those numbers underneath your line, outside your half box, make sure your degree drops by 1. Right? We don't want to hold on to x cubed anymore. Since we're dividing by x plus 1, all of our degrees will drop. Make sure that you are still following through with your integral rule, power rule for the first few terms, and the last term will just be natural log. And now that we worked through this problem, I want to go back to number 4 and show this problem here, and show that this is basically a variation. It doesn't quite have a higher degree in the numerator, but the degree of the numerator is the same. You can go through your substitution for number 4, but it ends up being a change of variable problem, which I think it's a little bit easier with synthetic division with this one. So let's do the same process with number 4. It just feels strange because the numerator has just so few terms there. One for x and the 0 for a constant. There's no constant, but I'm going to have a placeholder for that constant. Okay, bring the 1 down, multiply by the factor in front. So we already were at degree 1. So now this is just a constant and a remainder. So the integral of this problem here is just 1 turning into x and then a natural log that portion. All right, number 9. Too many terms in the denominator. We can't split up. This doesn't quite fit synthetic division either, because it's got to be a linear term. It's got to have a certain look to it, right? But we do see a set of parentheses. Looks like this would be a good fit for use substitution. So I like to have that dx hanging out outside of my fraction here. So let me write it this way. Okay, u value inside the parentheses. Make our substitutions. Push the coefficient out in front. Right, everything is nice and clean. No x's, coefficient out in front. What rule do we use for this? This is natural log rule. No, right? This is u to the second power. We got to bring this up and we got to go through a power rule. Right? I know it's tempting to go through natural log because that u in the denominator also feels easier to do adding adding with the exponent, just make it natural log, but we can't do that if it's degree 2, right? We only do that if it's degree 1. So we got to go through an additional step, make it u to the negative 2, and then go through power rule and then bring back your x. Right, so this is a potential trouble spot, especially if you're assuming that every u variable in the denominator is going to end up being natural log. All right, number 10. This is integral of 5 to the secant of x, secant x tangent x dx. This is a rather complicated setup, but we know this is going to be u substitution because we know that there's no single rule that looks exactly like the one that we're looking at here. And so our target is, what's our u value, right? What's our u value? we see this is base 5. It's not base e. This is base 5 raised to a variable. If I have a constant raised to a variable, that's an exponential function. This is base a. So we can use that base a to the u rule if it was 5 to the x, or 4 to the cosine of x, or 2 to the x minus 3. Anytime I have a constant raised to a variable, that's an exponential function. So this is going to be matching this a to the u rule here. So our exponent is going to be our u value, so that we can get it to match the rule that we're going to target. So our u value is secant of x. If we think back on first semester derivative, secant's derivative is secant tangent. Cross multiply. We make our substitutions. Secant gets replaced with u, dx gets replaced with u over secant tangent. That's a perfect fit. Now I have the natural log of 5 in the denominator, but we can also write it this way. We know the rule for a to the u is 1 over natural log of a times a to the u plus c. So you can either have that natural log of 5 below in the denominator, or you can push it out as a fractional coefficient, and then replace the u back in terms of x. Okay, these are the same, so just whichever form you're preferring. All right, 11. So this looks like it could be a good, well, first off, we ignore the bounds, right? The bounds is not going to play a role until after we're done with all of our calculus. So this looks like, well, I see base e. This is a messy exponent here, so why not let this be the u value? So we'll let the entire exponent be the u value in hopes that this x will cancel out later. Sorry, no, I don't know why I put plus c. It's dx, my bad. Okay, go through u substitution. X's cancel out. We need that to happen, but there is a negative that is going to stay with our integral. Right? We know e to the u is just a nice e to the u. We know e to the u is not going to change. Right? Integral of e to the u is just itself. Drop the integral, drop the du, replace. Now we have our antiderivative. Replace the u back in terms of x. Now I can do the half bracket. Now I can plug in the 0 and root 2. I do want to point out something about 0 here. I think we're going to maybe assume that 0 is always going to wipe out everything. It does wipe out at least a portion of what we're plugging in, but it may not wipe out everything. So just be careful with zeros that you're taking the time to plug in and actually confirming that it may not wipe everything out. So in this case, the 0 gets plugged in for the exponent. The exponent goes to 0, but anything raised to the x to 0 is not zeros. It's 1, right? So this becomes plus 1. And this becomes 2 times negative 1/2, which is negative 1. So I have negative e to the negative 1 plus 1. This is fine, or you can say negative 1 over e plus 1. All right, so your homework is back with your homework packet. We didn't get a chance to do that a to the u homework problem, so our homework is pages 5 and 6. From your homework packet, make sure you can locate that. It says 7.2b exponential base a. I'll send out a reminder this afternoon. I'll check this for homework, and then we'll just continue working through our quiz review. All right, come get your phones.